Okay, we have started the recording. So good morning, everybody, ladies and gentlemen. We're very welcome to our next session. It is already session number 9 on photovoltaic systems. So we've done well. We've come from a bit far now, and I think we are enjoying this course with discussing the possibilities and the experiences of PV photovoltaic systems from different angles. So thank you very much again for joining us. Today we have prepared a session that is going to be mostly around the case of small or medium grid connected PV systems. We also call them rooftop PV systems because they are normally installed on the roofs of existing buildings. So it is a very interesting application of solar systems because we can retrofit them, we can adapt them and integrate them, especially in the urban areas where we already have some buildings, and we can add PV systems to them, and of course conveniently integrated into the electricity systems or the grids where these buildings are placed. Today I have with me a colleague, engineer Arnau Alarcón. Arnau, you can say hello.
Good morning, everybody. It's a pleasure for me to be here.
Thank you. Arnau is an engineer with 20 years experience. He has done many solar projects, and I have asked him to join us because he will also he has been working with me in different projects, and he has very good examples to show specifically for this type of PV systems. So today basically we are going to look at a couple of real projects that basically Arnau has been working on. Two examples of this kind of projects, grid connected rooftop projects, and we will be looking at them in very much detail. All right. So thanks Arnau for being here. The usual scheme we are going to follow is that we have more or less 50 minutes or 1 hour session. We will cover hopefully one of the examples, then we have a short break, and then we continue with the other example. Okay, so let's go for that. Just a reminder, the kind of recipe that we follow or we like to recommend for energy projects. Remember always the integrated approach for the planning. We have social development component, we have the organizational component, we have and within the organizational, of course, the different roles, responsibilities, different institutions that are involved in a project. Then we have the technical or technological component and the economic and financial. Yeah, so that's pretty much at the beginning of any project, this integrated vision of the project. Then the site assessment, energy demand assessment, if that is relevant, very relevant for off-grid projects, for grid-connected projects, could be relevant or not. We will see that today. The concept of our project, the configuration, the topology, etc. Then we move into precising, even modeling. Then we can define the outputs, the inputs, the bill of quantities, the budgets, etc. And finally, we take a decision to go ahead with a project. That's when we select and eventually launch the purchase, procurement for the equipments, components, and of course the operation and management aspects of our project. Just to remember, when we consider the grid connection, the connection of photovoltaic systems into the grid, then we come across normally a series of regulations that have to be observed, and that depends normally on each country And there are different layers. Some of these regulations are more related to technical or technological aspects of the grid codes, etc., the integration into grids. Some of these aspects are more administrative. Some aspects are related to the financial condition of the photovoltaic projects, especially if we are in a situation where our regulations they allow some kind of payment or retribution for the electricity that is being injected into the grid. Feed-in tariffs, power purchase agreements, etc. This was a slide that we shared a couple of sessions ago, if you remember. This is the situation in Spain. So in Spain, the legal framework for grid connection of photovoltaic systems defines up to 8 different configurations. And we have up to 7 different regulations depending on the kind of system that we are thinking of, whether it is on-grid or off-grid. And if it is on-grid, we can have the power, the photovoltaic power plants, whether they are small, below 100 kilowatt or above that level of capacity. Then you have different decrees, different regulations. So the policy and regulations aspect are of course of application in our projects. Okay, so having that in mind, the projects that today we want to share with you are located in a place that we know very well, Arnau and me, which is our home city of Barcelona. This is actually where we are now, where we are sitting and speaking to you. We are in Barcelona. So we're going to tell you about a couple of projects. One was done, designed in 2014, so it's now a little bit older, in a cemetery in this area here, more or less, very close to Barcelona football stadium. Those of you who like football, so you will see a little bit. The other project is in a big tunnel that is underneath a little mountain we have here, a little hill. You can see these green spots here. So there is a tunnel that goes underneath a hill here, and there's a PV project that was designed by Arnau a couple of years ago in that location. Okay. So okay, Arnau, as we said, anytime you feel free to come in.
Okay.
When you want to make any comment. I'll be asking you some stuff, okay? But if I miss something out, or just feel free. We are all colleagues here to come in and have your say. All right.
Okay.
Okay. So the first case, the cemetery in Las Corts. Basically, the goal of this project was to improve the self-sufficiency of this. This is a public cemetery, okay? This is a public facility in an urban environment, served already with the grid, and there was a certain availability, okay, of space for the photovoltaic system. It is a very special case because at that time in 2014 the regulations in Spain were very restrictive, okay, for the connection of small systems to the grid. So Arnau and team had a very clever idea to come up with hybrid system, even if it is grid connected, okay, but to include some storage in this system, okay. I don't know, Arnau, if you want to add something. Why was this project like originated? What was the idea behind this?
Yes, this project comes from an ambitious plan by the Barcelona City Council to promote renewable generation in the city itself. This plan was called the Energy, Climate Change and Air Quality Plan of Barcelona 2011-2020, and included, among many other things, the execution of a large number of photovoltaic installations for self-consumption in different locations in the city, like Paul said before. The installation was developed in a public tender format, and the engineering works, which are the drafting of the executive project and the construction management and the implementation, were tendered separately. I was in charge of the team responsible for the drafting of the executive project and the construction management. Like Paul said, in 2014, in Spain, it was a bit difficult to do photovoltaic systems because we had a lot of restrictions in the law. And this is the reason why we decided to do this kind of installation. This photovoltaic installation is a type of installation called grid assisted. And this means that it has the grid as a support system. But the photovoltaic installation and the grid can never work in parallel because it was no legal. The consumptions are fed either from the photovoltaic installation or they are fed from the grid. The system has a switch that is in charge of commuting between a system or another. And the installation is sized to cover 90% of the cemetery's energy demand. And after 6 years of operation, this objective has been achieved. Specifically, I remember, I think that is 92% of the time, the installation is operating as an isolated installation without needing the grid. And 80% of the remaining time, the consumptions are supplied 100% by the grid.
Okay, thank you. So it's a very good example of what this flexibility and adaptability of PV systems can offer that we have mentioned many times. At that time, the regulatory conditions in Spain were very restrictive, but there was still a way, to connect a small system into the grid without, at that time, the fear from the government or the big utilities was that a large amount proliferation of small PV systems could affect the grid somehow, and also introduce some problematics in terms of the financials of the grid. So now this is changed. Now in Spain, all of this has been solved, and now it is much easier. But at that time, it wasn't so easy. Okay, so remember, for rooftop systems, the placement, the layout of our PV systems, the modules are going to be essential, because we already have some roofs. This is the case of the cemetery. The cemetery is already built there. So we need to adapt to the existing building. Roofs, sometimes it's a car park, sometimes it's some kind of wall or facade, okay? Of course, we are in the middle of the city, Barcelona, so the shading is critical. The type of surfaces we have might be more convenient or less convenient to support the PV modules. And then some other structural conditions, the accessibility to the buildings, for the maintenance, etc. They are also factors of decision in a project like this. Also, the grid connection considerations. The maximum current rating that can be dispatched through the existing connection. Distances, the routing, the different cabling or electrical layout that we will have to come up with, from any switchgear to interconnection points with the utility, with the electricity company, the existing service panel in terms of current voltage phasing, how old that is, the condition that it is in, the available space for more electrical connections, and obviously the utility metering regulations and requirements. So this is, as I told you, this is Barcelona football stadium. This is here. This is where Messi and his friends play. And this is just behind it. We have some university campuses here around, okay? And this is the cemetery. we are talking about. This is the district of Las Corts. All right. So we are in Barcelona, latitude, longitude, and it is a grid connected system. This is a sketch, this is a map, ground plan of the cemetery. See different buildings. And this is the area where the project was selected. Yeah, these are the group of buildings that the municipality asked the team to think of. Why, Arnau, why was this buildings here chosen? I can see it's quite close from the entrance. That's probably a good idea. But were there any other factors to choose these buildings here and not many more?
Yes, the other reason is because the place for the batteries is close, is just below one of these buildings, and we wanted to reduce the piping distance and the cable distance, and also the connection to the grid is close to this zone. And it's important to mention that this is a 19th century cemetery, and this protected because it's very, very old. And all these buildings are very, very old, and some of them are in bad conditions. And we had to be very carefully with the buildings that we act. And we decided with the people who is working there to use these buildings because some years ago they had a works for replacing them because they had a lot of problems in the roof, and these were the buildings that were in a better state. Right?
Okay.
Barcelona, with this installation, when this facility wanted to be one of the pioneer cities in the creation of microgrids inside the city, because this is a small microgrid, and the Las Corts Cemetery was chosen to carry out a first pilot test because it was a building with a moderate energy demand, and which allowed achieving high self-sufficiency with a moderate installed power. It should also be known that the photovoltaic installation was part of a global energy efficiency project in the enclosure, which also included more things like a solar thermal installation, the replacement of all the lighting system by LED systems, and also the renewal of the air condition equipment. And later, some similar projects were made in other locations in Barcelona. But specifically, these buildings were proposed for the managers of the cemetery.
Okay, thanks. So okay, those buildings had some optimum, let's say, conditions in this cemetery. It is important to highlight what Arnau said. It is an old place with some historical buildings, of course, very sensitive buildings. It's burial grounds, some small mausoleums. So it has to be a very delicate work to be done.
Yes, this was one of the most important things of the project.
Exactly.
We had to be very, very carefully because it's an old and historical building, and we had a lot of eyes looking to us.
Of course, a lot of care. It had to be a very neat installation, etc., and very well integrated. So one of the first things that are now checked was the availability of the surface, and it was something between 380 and 400 square meters, okay, of space for PV modules. Okay, so that's the conditions of an existing building. A certain amount of square meters of surface area, and you have to work with that. This is one of the inputs for engineering work. So this is the layout. You can see the buildings are more or less with a rectangular ground plan, and there was a convenient orientation towards the southeast. Okay, so being Barcelona in the northern hemisphere, of course, that's convenient for an orientation looking at the southeast in this case. Okay, well placed in that sense. The orientation minus 22 degrees, slightly towards the east with respect to the pure south, and no nearby shadowing elements. That is important. Here we see a picture of the buildings. These are the burial niche, okay, or the cemetery, and we can see the buildings. Okay, there's a little bit of snow.
In this case, Paul, sorry, the architectural integration of the modules was very, very important because, like I told you, it's a 19th century cemetery and is protected. And for this reason, it was necessary to work to keep visual impact of the modules to a minimum. To achieve this, it was decided that the modules that were in a more crowded areas had a 10 degrees inclination, which is not the most optimal, but it does prevent them from being seen from the ground. The rest of the modules are inclined at 30 degrees, like Paul said, which is the optimum inclination for self-consumption facilities for Barcelona's latitude. Due to these different orientations and inclinations of the modules, the connection of the strings had to be very carefully thought out in order to reduce losses as much as possible and for the MPPT trackers to work in good conditions. Remember that all the modules connected to the same MPPT tracker have to be at the same orientation and inclination. This is only what you were talking about, the orientation and the inclination, and we have to be very carefully with this.
Exactly. Okay, then of course the solar radiation in Barcelona was checked out. We are, those of us who work regularly in solar systems in here, we have a lot of data already, but more or less Barcelona, we have on average this kind of radiation, less radiation in our winter, which is now January, February. Then we go to the summer, which this is where you are now in Maputo, Mozambique. You are in the summer now. For us, the summer is in June, July, August, and then coming down to winter again. So the electricity demand was investigated, was analyzed by Arnau, and they concluded that more or less a total consumption of about 190 kilowatt hour every day, on average. That's an average. Was taking place in the cemetery, basically due to the administration building, obviously the offices and the facilities there.
Mostly for the air conditioning systems.
Yes, for the air condition and the climatization, the heating and ventilation and the climatization, the building. Then there is a workers building and some outdoor spaces, some lighting and some surveillance, etc. But essentially from the administration. So all in all, we can assume a demand more or less flat of about 5.6, 5.7 megawatt hour per month. Okay. And remember what happens when we have a PV rooftop, a grid connected system. We will have a certain demand, that is a black line for a given place, okay? And then when we consider a PV system, we will have a certain generation. When the generation happens during daytime, a lot of sun, a lot of generation from the PV modules, that could exceed, okay, the consumption at that moment. So in this area here, where the solar panels are generating, but we don't have consumption, we have surplus energy. We have a lot of electricity being generated by the panels that is not consumed at the moment in the cemetery. If we go for higher PV system, we will even have, of course, more excess electricity. And this is where we come with our configuration. What do we do in here? We can either inject it to the grid, or we can try to keep it. Okay, we can try to store it. Remember, at that time, 2014, the conditions of injecting electricity to the grid were not favorable because there was no economic return.
And sometimes it was forbidden.
Exactly, and what it was forbidden under some circumstances, you could inject it, but it was not. You will never get paid for that. You would have to prevent injection. In some cases, it was a nightmare. So, in this case, the project in the cemetery decided to add the batteries, okay, to be able to store and not lose all this generation here, okay. Now, as we speak, the conditions in Spain are different. Now you can inject and you can get paid under some regimes. These are some considerations that we made a couple of sessions ago about the self-consumption and the solar fractions. You remember there's always a minimum, a maximum size of a PV system that will give you the optimized self-consumption ratio. In our case, let's go back to our case. Taking into account these two design factors, the availability of space and the amount of electricity that the cemetery was consuming during the year, the design finally came up with this solution, considering some interruption. Okay. Oh, okay. Please remember to mute your microphones unless you have a question. Thank you. So I was saying, considering the availability of space and the amount of electricity that the cemetery is consuming during the whole year, the calculation of roughly 58 kilowatt peak came up as the needed installed PV power. Arnau was checking different types of PV modules, specifically the brand Bauer BS6P22 with a size, a module capacity of 240 watt peak per module, and taking into account the area that was covered by each module, all in all came up with a solution of 240 modules of 240 watt peak each. That will give us a total installed peak power of 57.6 kilowatt peak. That will yield, that will generate 112%, so slightly above the electricity consumption in the whole year. So this means that there is a possibility to store electricity in the batteries and even to have some excess electricity in our generation for some eventual malfunctions or some losses that we can cope for. Okay?
The capacity of the modules is improving every year a lot, because this is but in this year 2014, 2040 watts peak, it was a good performance for this module. But yes, now we are working with modules about 380. But
380 for a similar area, or a bit bigger, but much more.
Yes, no, very similar. Only 0.1 square meters more.
Yes, much more.
The global efficiency of the modules is improving a lot. If you can see here, we have 14.7% of efficiency. Now we are talking about 2021.
Yeah,
we are improving a lot.
Exactly. So now, if we had to do the same project we could have less PV panels for the same production, or we can, for the same roof area, we can even produce much more and then sell to the grid.
Yeah, maybe 25% more.
So yeah, some more pictures are now, if you want to comment any of the things. This is a final layout with a structure with some prefabricated.
You can see at the end of the picture, the so far away place, you can see the modules that are at 10 degrees inclination. Here, where Paul has the mouse, here and in front of these modules are at 10 degrees for this reason of the visual impact that I told you before. And the others, all the others, are at 30 degrees inclination. That is the optimum for our latitude. And also we use these structures that that is from stone. For we cannot do holes in these buildings because it is not possible to. If imagine that it's raining, we have to take care with the water, and this is the reason why we decided to use these big structures of, I don't remember the word, Paul.
This is prefabricated. This is concrete slabs. Yeah.
Concrete, right? Yeah. We had to use these concrete slabs to ensure that we are not making any hole in the buildings, because we have to ensure that if someday it rains, we will not have water inside the buildings, because like you can imagine, will be a big problem.
Exactly, the cemetery. Okay, so then once the concept of the system was defined, then now that's when you used some softwares, to model.
Yes.
Okay, and in this case you used the PVSys. It was 2014, so a bit old project now, but you chose to use the PVSys because it's convenient, quite flexible, right?
The PVSys in 2014, it was the common software to calculate PV systems, and it was a good tool, because it's very flexible, like Paul said. And I was using this software many years, and now, like we will see later, I am using another software called PVSol, that for me is much better, because we can work a lot in 3 dimensions. That it's better for example, for the shadowing. For me, it's quite better, and also for the data of radiation, that we have a data radiation of all the wall, and with PVSys, in some places it's difficult to find this data.
Okay, some more details of the project. In each building, you had different strings of different lengths, and then for the power conditioning, the solution from SMA, in this case, the 3-power 10,000 TL was selected. Okay. 1 inverter per string, so you had 5 inverters because you had 5 strings. Okay, and well, these are the characteristics of the inverter. I don't think there's anything super duper about this. Good product, and
this product is very good for working outside. We didn't have space inside the building for installing the inverters, and we decided for this model because it can be installed outside, and they have no problems with the radiation and with the rain, and they adapt very good to the climate conditions.
Good. And then what it is worth mentioning is this element here, the microgrid manager, because in this configuration, in this grid assisted, as we said, let me jump ahead a little bit. It is important to understand that the role, yeah, of this central element. This is the brain, let's say, of the of the solution that can manage both the consumption from the grid, if necessary, okay, from the PV systems coming this line, or interacting with the batteries. Yeah.
So you can see the switch element inside the microgrid manager. You have a switch that choose if we use the grid or if we use the photovoltaic installation.
Correct. So for this specific system, this component was necessary, manager component. Now, the storage, the batteries, as we mentioned before, in a system like this, there's a lot of the time where in a day where the PV panels are generating and there's not enough consumption. So typically, the optimum working point would be somewhere here. But if we add batteries, we can increase the self-consumption ratio, because we can keep part of the generated electricity and consume it later on in our same place. So this was the purpose of the batteries, to increase the self-consumption ratio. The design of the batteries, of course, you know how to size your batteries, taking into account depth of discharge, type of batteries, days of autonomy. We've been talking about this now in this course already. So yeah, this was the battery that was finally selected. Okay. Yeah, working at a rated voltage of 384 voltage in DC, and a total bank capacity of 320 kilowatt hour. Okay, and they were sized and specified in C20, and capacity rated at a discharge time of 20 hours. I think also it's worth mentioning, yeah, for the case of this configuration, the fact of having the grid is so convenient to help in the equalization of the batteries. Hello? Let me just deal with this. Now, are you there?
Yeah.
Okay. I was saying that the fact that we have the grid is convenient for the equalization of the batteries, right?
See, the equalization of the batteries is very, very important. And in this case, the microgrid manager is programmed to launch an equalization of the batteries once a month, every month, from 12 to 8 a.m. when the energy from the grid is cheaper.
Okay.
To perform the equalization, the microgrid manager commutes with the grid, since it has a much more stable behavior than the photovoltaic installation. In this way, it contributes to considerably extend the useful life of the batteries. It's important for the maintenance of the batteries.
Exactly. Remember, for the lead-acid batteries, we have different stages in the cycling, in the charging cycle of a battery. We have a first stage, yeah, deep charging. Then we have a topping charging stage, where we want to keep the voltage constant. This is battery being charged by the PV panels. And then we have the float charge, where we keep the voltage of the batteries between a certain range of values. So these are the 3 stages that are generated by the PV panels and controlled by the charge controller. But every now and then we still need a 4th stage we call the equalization charge that is recommended by all manufacturers, and it's very useful to keep the well-being of the batteries, to align them, to also prevent the deposition of different elements in the batteries, especially in batteries that have not been fully charged for a long time. Some stratification in the electrolyte can happen, and that can damage, little by little the capacity, can reduce the capacity of our batteries. So in this case, in off-grid situations, the equalization can be boosted with a generator set, but in this case of the cemetery, we can use the grid, okay, to do this boost charge, the equalization in the batteries, and even program it, as Arnaud has said. Okay, so yeah, the PV Syst was very helpful, okay, in providing different modeling and different information, the losses that could be expected, the different.
It's very useful also for the connection of the strings.
Yeah. Okay.
To be very carefully with this, because we need to adapt the output voltage of the string with the input voltage of the inverter. If we go out of this input voltage of the inverter, we can have problems with the production of this inverter. And PV Syst is very useful with this configuration.
Okay, month by month, you can see the estimated productions and performance of the system, the different losses, estimated. This is all estimated, the model. Okay. The single line diagram, as we mentioned,
with this diagram, it's important to mention that the microgrid manager is programmed so that whenever possible, consumption is covered instantly by the photovoltaic installation without going through the batteries. Yeah. This is what is called instant self-consumption. And when photovoltaic production exceeds consumption, the surplus is used to charge the batteries. As the photovoltaic production decreases, the batteries begin to supply energy. When there is no sun, the consumptions are supplied 100% from the batteries. And if the batteries reach their maximum depth of discharge value, which is around 60%, I think, the microgrid manager switches to the grid with the commutator that we have inside.
So this is the main board of this is the entrance to the consumption, and it can be fed from the photovoltaic system, batteries, or the grid itself. Okay. These are the details of the 5 strings. This is the string 1, 2, 3, 4, and 5. This is details of the engineering project. Each string, as you can see, conveniently analyzed with the maximum expected currents and voltages per string. Okay, finally, some final considerations. The self-consumption ratio expected roughly 90%, and only imported electricity from the grid 10%.
This is the expected, but the real one is 92%, because we had a system to monitorize the demand and also the production, and we are achieving 6 years later 92% of self-consumption ratio, autosufficiency ratio.
So colleagues in the room from EDM, from Mirem, Funai, of course, AREN, and private sector, you see, with a solution like this, in the end, you reduce the consumption from the grid to just 10 or 8%. Okay, so you become 90 or 92% totally self-sufficient, independent from the grid with your solar PV system. So in a country like Mozambique, for the buildings, for residential buildings, commercial buildings, public buildings, we think, right, Arnau, this is a great approach that we invite you to consider for Mozambique. So more pictures you can see working in the roofs of the cemetery, the different concrete slabs, carefully designed to to generate those slopes, for each of the buildings. Each building had its own particularities. And finally, some references. The budget, of course, the money, always important. So we can find a reference. This is from 6-7 years ago now, but we find this reference of 213,000 euros, more or less.
How long to recover the investments done in that project? Good question.
This is more or less an investment cost of about 3,600 euros per kilowatt peak. Okay, so for a grid connected systems with batteries, let's not forget that there are batteries here. It's still quite a good investment cost. Of course, now we could do it cheaper than that, but the batteries are an important part of the budget. If you see the cost of the PV panels and inverters, 74,000 euros is not that higher than the batteries only. So if you can do this with smaller batteries or even without batteries, then the investment cost,
like Paul said, now here in Spain, without batteries, instant self-consumption, you can recover the investment in 7-8 years. It's a realistic number, but you must think that the life of the installation is above 30 years, and you have 22 or 23 years of totally free energy. And with the batteries, this you can recover the investment, the payback of the installation. In this case, I think that it was 12 years, 12 or 13 years. Now they are still paying the investment.
Can I have a question?
Yes, of course.
Yeah, of course.
Yeah. My question is that the plant is to be a life of the plant is 30 years.
Yeah.
Right.
Yes.
And life of the battery is not 30 years, is it?
No.
The life of the batteries depends a lot of the maintenance, and of the use. If you take care of the batteries, you can extend a lot their life. And doing this equalization that we were talking about before, but here in this case, we expect 15 years of life of the batteries. But when these batteries die, 15 years, we are expecting to use the grid as a battery. We are not expecting to install new batteries, because we hope that maybe in 2030 we will be able to use the grid as a battery. That is what we wanted to do, but it was not possible. We can put the surplus of generation to the grid and use the surplus during the night without using batteries. But we expect a life of 15 years for this battery.
Fantastic. So you in Barcelona did not manage to sell and buy from the grid?
Now we can, but in 2014 was not possible.
I think
now we can
Kamal,
use the grid for putting this surplus.
yes, we had a very unfortunate regulation, yeah, in the previous two governments before the current one. Yeah, it was very very polemic, controversial.
Yes, the most restrictive in the world, the people say.
Yeah. So there was a huge fight, regulatory fight against that, and now it is completely solved. But it was yeah, a lot of political. It was a political vision to obstruct the possibilities of small systems like this one. And well, luckily now these things have been overcome. We have
Sorry, Paul, somebody is asking
a question. Yes.
Who have financed the project?
Okay.
It was a public installation. It was paid by the Barcelona City Council, 100%, with public money.
The client here, Enriquez, there's a question from Enrique Senda. The client here is the municipality of Barcelona. But let's not forget, Enriquez, because the municipality of Barcelona was also paying the electricity bill. So the fact that it is the municipality of Barcelona public administration doesn't change. If you were a private, you will have to act in the same approach. The municipality does an investment, but then will save 92% of the electricity bill for a long time. So there is economic interest. In fact, when there is a public institution, it is normally easier to accept financial projections where you will have a return on investment which is longer than 6, 7, 8, 9 years. Because as a public institution, you can afford longer payback periods. A question, the cost of electricity in Barcelona. Okay, in our tariff we have two terms. One term is for the power capacity, and one term is for the electricity, the energy demand. Arnau is replying for the energy tier, the energy term, which is 14 cents per kilowatt hour. We also have a fixed charge per.
Yes, we have different prices, but this is more or less.
This is the tariff for low voltage consumption, the commercial residential tariff, more or less. Okay. So we can move on. The budget, as we said, this is a bit of an old project. I mean, 6, 7 years now. If we had to do the project now, the financials and the system would look more optimized and even better.
Of course.
Even at that time, it was a very good idea, and the experience with this system is very, very good. Everybody is happy with that. We can take a small break now for 5 minutes. Dr. Lucas, do you agree?
Yes. 5 minutes break. It's okay.
Is that fine? Yeah.
Yeah, it's fine.
Okay. Thank you very much. We are coming back in 5 minutes with another case study in Barcelona, close to Sagrada Familia this time, but this is after the break. So thank you. 5 minutes.
Okay. Thank you.
Let's continue after the break. Okay, you can see the screen correctly, right?
Yes.
Excellent. Okay, so thank you. Welcome back. We are going to have a look now at The second example, this is also in the city of Barcelona, and it is a tunnel. It's a car park actually close to this tunnel. As we said in the introduction, this system was designed a bit later than the previous one in 2018 with a new regulation in place, not so many difficulties to connect PV systems into the grid here. So it was from that point of view easier. And this is why the goal, the approach of this project was different. Rather than self-consumption in a particular building, to make use of a building with a lot of available space to generate electricity and inject it to the grid mostly. Okay.
Yes,
so a grid connected.
Paul, sorry.
Yes.
The objective of this installation is to increase the generation of energy in the city itself and increase the amount of renewable energy introduced into the electrical grid. Remember that each kilowatt hour produced in the city does not have to be imported from a power plant located maybe hundreds of kilometers away. Yes. And it was also promoted by the municipality of Barcelona and was part of a big remodeling of an urban area.
So again, we have the public institutions here as the lead developers of a project, of a rooftop project in Barcelona. Yeah. So this is another area of the city. We can see still the sea here, the old town, Barcelona. We have the Sagrada Familia Cathedral. And then this is the little mountain area, hills that I told you. And this is the tunnel underneath. There's underneath this little hill here, we have a tunnel. And this is where the system was projected. This is an underground tunnel, and there was a building at the entrance, at the south entrance of the tunnel. Yeah, big car park with a long surface area available for that. So since the approach of this project, the concept is more of a net generator facility. In this case, the assessment of the electricity demand was not necessary. Okay, so we can skip exactly this step in our recipe for project design. Again, remember orientation, inclination, tilt, shading, surface type, the building conditions, technical conditions of the grid connection. The same aspects that need to be considered in our project. So this was the site. There's as I said, a big roof, available for that. Again, the orientation southeast, right? And quite similar orientation as the buildings in the cemetery that we saw before. The roof, okay, flat roof, very stable structure, no problems of accessibility or limitation created by other ventilation or AC equipment. So it was quite of a convenient surface, right, to work with. No big obstacles, so good availability of space for the consideration of PV modules here. Again, consideration of the solar resource had to be checked and properly reported in our engineering design. And the calculation of the PV power. Of course, in a surface like this, now you have to think a little bit how to place the modules, right? Because you can put many of them, but you need to be careful with the shading between the different lines. Yeah, correct?
Yes, we have to calculate very good the separation between the lines. But at the same time, we want to produce much more energy than we can, and in this case, the client wanted to take advantage of the space a lot, and we had to think a lot about the separation between the lines, and we had a first proposal of modules in the surface, but the client told us, no, we want more power, and we had to recalculate for taking advantage more of the space. And in this case, this meter that you can see in this picture, this meter of separation, it's a short separation, and we also we helped with PVSol, that is the software that is better for me than PVSys, for doing calculation, a very good calculation of the shading, for reducing this distance between the lines, for to get a big more power in the same space. It's important to think about it.
Yes. You mentioned now the use of PVSol, huh?
Yes,
one of
the PVSol is very good because it works very good with the 3 dimensions. You can draw all the modules in 3 dimensions, and we have a specific tool to calculate the shadows and to get the losses that you are having for the shadows. And thanks to this tool, we can adjust very good this distance between the lines for having no shadows.
Yeah. So remember, ladies and gentlemen, we did this exercise, yeah, in session PV05, where we mentioned
yes,
how to
you can do it with trigonometric calculations.
Yes, exactly. How to optimize, yeah, the distance, because obviously when the sun is low, remember, the sun will hit our first panel, and the first panel will necessarily be shading the panels behind the first one. As the sun rises, then this shading disappears, and finally the sun is hitting all the modules clear. So it is yes, a very fine calculation. In your calculation are now obviously with the modules so much packed or close together, when the sun is low, there will be a higher degree of losses than when in the winter time, than when the sun is higher in the summer.
The problem is only in the winter.
Yes,
because in the summer is no risk. There is no risk of shading or of losses. The only risk in the summer is the high temperatures.
yes.
That when we have high temperatures, the voltage of the module go down, and we can have problems of low voltage, but not shadowing, not shading. Sorry.
Exactly. So yes, with the total area surface of 470 square meters, a number of modules that could fit there, 285, but these modules are a little bit more efficient, yeah, than the ones we saw for the cemetery. Remember, the ones in the cemetery were rated at 240 watt peak per module. This
is 4 years later.
4 years later, we have an improvement. The efficiency, remember, it was 14%. Same kind of technology. Yeah, we're talking about, is it polycrystalline? Yeah, polycrystalline, silicon technology in the modules, and you see 4 years later, the efficiency had increased from 14
yes, to 2%.
Exactly.
In 4 years.
In 4 years. So for the available area surface and with this type of modules, a total installed power capacity of 78.4 kilowatt peak was possible. Here we have a nice drawing on the different strings. Yeah, a total of 18 strings of PV modules you have here. 15 strings composed by 16 modules and 3 strings composed by 15 modules. Yeah. Now that we're talking about this, more or less, how do you, if you can share with us in the session, how do you decide how many modules you will put in one string or another? What are the main arguments or factors you consider?
Yes, to decide the number of modules for each string, you have to check the input voltage of the inverters. You have a rank of voltage, and that is the output voltage of the string. And in this case, you can see, for example, on the right, that you have one string only with the model, this red string, the models in red. They are all in the left side because you have a wall in the left. This is a wall, and in some hours during the winter, we have shadows for this wall. And we decided to put all the modules that are affected for these shadows in the same string. And this was the concept of all the strings. When we have modules that are affected for some things like back inclination, back orientation, shadows, we have to put these strings, these modules, in the same string, because we don't want affectations. Because if I put a good module connected with a bad module, all the modules will work like the worst one. And exactly. We have to be very careful with this. And when you have in the inverters, like I said before, we have this range of voltage, input voltage from the strings. And this is a large range, maybe 300 volts, 700 volts. And it's good that the output voltage of the strings is in the middle of this range, maybe 500 volts in DC. And this is how I decide how many modules is in each string, because I have to increase the voltage of every module. And if I have 18 modules, I have to take in care that is the voltage of 18 modules.
We see. Very thanks for that. This is an issue that, if you remember, we also mentioned for the session on large plants, yeah, for the solar farms or solar parks, because in this example we have was it more or less 285 modules. Now, imagine a large PV farm where you can easily have thousands of modules. So this same concept is very much of importance. In here, Arnau is telling us about the effect of some minor shading. The sun will do a path something like this. Yeah. From
yes,
the east,
in the morning.
from the east, in the morning, yeah. So when the sun is low in the winter, here this wall here will cast a bit of shade on these modules here. In the case of the solar farms, we were talking about even the slight differences of quality of each module. From the flash test reports, modules are not manufactured exactly the same. Even if they fall within the tolerance of what is accepted as a proper module, there can be slight differences in the production of each module. 1% more, 1% less. So yes, this same engineering approach that Arnau is telling us, the same that we were commenting with in the session of solar farms. So the bottom line here is that the decision of which modules to put where and how to connect them needs some thinking so that we can optimize the overall yield, overall generation of our PV system. Okay. Selection of inverters, again, the same good old tree power, but in this case of higher power capacity. In the previous example, we saw, or now that you chose again sunny tree power. In that case, you had 5 inverters, 1 per string. In this case, you decided to go for bigger inverters and connect different strings, 6 strings per inverter. So
yes,
you still
because
have
each inverter has 3 MPPT trackers. And when you decide which inverter do you want, you have to look at the MPPT trackers. And this is one of the reasons that I choose this one, because I have a lot of flexibility to connect these strings with these 3 MPPT trackers.
okay. So it's in fact you have like 3 MPPTs in each of these ones, so you can connect you can combine them. So you have 18 strings connected to 3 inverters.
6 strings for inverters.
Excellent. So that's
and every MPPT tracker has 2 strings in parallel, connected in parallel.
okay. Okay. Yeah, specifications of the inverter. I don't think we have more issues to comment in here. The output of this inverter, we have it here, the output conditions. You chose this model here, 25 kilowatt, yeah?
Yes, and because we have 78 kilowatts peak of modules.
Exactly.
I also choose a little bit less of inverter power. In this case, 75. Is 75.
Okay. The output of the inverters was in 3-phase, right?
Yes.
So 3-phase output. Excellent.
It's 400 volts.
400 volts output. Okay, this slide is a little bit small, but because the single line, the diagram is large. Sorry for that. So you can see, that's the general configuration of the system. We have all the PV module strings here. Each string again clearly identified. Okay, with each of the protections, and then going into each of the 3 inverters. We have for each inverter we have the 3. You can see the 6 strings going into each inverter, then the protections, and then going into the connection with the utility. With the metering and into the.
Can I have a question about the 3-phase inverters?
Sure.
Yeah. If you can let me know. Yeah, this is the 3-phase inverter, right?
Yes.
So the connection is done from each. If you go to the circuit.
Sorry? Can you repeat?
The circuitry that you have shown us. Yeah. So the 3 inverters are already there, right?
Yes.
And the strings, you mentioned about 3 strings plus 3 strings. Can you elaborate a bit more? Because if it was a monophasic, sorry? Yeah.
Every inverter has 6 photovoltaic strings connected, but they only has 3 MPPT trackers, and we connect 2 strings for every MPPT tracker connected in parallel, these strings, and this connection is in DC, direct current, and this inverter convert this DC in 3-phase AC, 400 volts.
Yeah, each of these inverters, Kemal,
we have no monophasic connection here. We have DC and 3-phase AC.
Each of these inverters has 3 input, okay, circuits. It has 3 MPPT trackers, okay, so it can create a 3-phase output, because internally, okay, it combines the 3 circuits. This is specific from this inverter and all the inverters that have a 3-phase output capacity, okay? So in an inverter like this, you need to connect at least 3 strings. But remember that electrically, each string can be created by adding, 2 or more strings in parallel.
Yes, this is
okay. Thank you. I got it. Yeah.
Okay. This is for the PV Sol, I guess. Yeah. Some.
Yes, this is from PV Sol.
Okay. The projection of the generation values from the horizontal radiation, the radiation in the inclined and the tilted surface. You can see there's already an increase by tilting the PV modules with respect to the horizontal plane. A provision on the air temperature. Is this expected? Yeah, this is the outdoor. And then the temperature of the modules, depending on the...
It's very, very important, the temperature of the modules, because it depends a lot the efficiency.
Yes.
Each module.
Yes.
More temperature, less voltage, less voltage, less power.
Correct. And finally, the amount of electricity that this system 75 kilowatt peak kilowatt expected to be generating and injecting into the grid. You can see the same PV system would be generating double the amount of electricity in the summer than in the winter, for a total yield of 109 megawatt hour per year.
Sorry, I have a question. Yeah, I feel a bit confused.
Yes.
You said the temperature. I always heard that the temperature, the warmer it gets, the less efficient the module is. But now you insinuate is the contrary.
No.
But I see that in the months of May, June, July, August, it's more insulation. That's why you get more wattage out. It's not because of temperature. Okay, it's not because of temperature.
Of course, it's not because of temperature. These two effects, Kemal, are balancing each other.
Exactly. Okay. Yeah, I got it. Yeah.
The most important is the level of irradiance. If you remember in the solar curves on how a PV module works, when there is a higher rate of irradiance, the IV curve of a module goes higher. The higher the solar radiation, the higher the current that is produced by a module. But if this module gets heated up, the temperature, then the voltage output reduces a little bit. Okay, so yes, in the summer there is higher production because of the higher irradiance, but slightly lower module efficiency because of the higher temperature. If you check the efficiency of the module, understood as the amount of radiation falling onto the module and the output electricity coming out of the module in the winter, this efficiency is higher than in the summer. But in the summer, the solar radiation hitting the panel, the solar module, is much higher. You see? So even though
this is the key, eh?
Yes.
The efficiency of the module in winter is higher than in summer, but in summer we have more and more radiation, and this is the reason why we are producing much more energy. But if we check only the efficiency of the module, is lower because of the temperature of the cell.
Exactly. So this is why, in practical terms, what happens here is that we need to make sure in the summertime, when we have high levels of radiation, higher temperatures, we need to think of a design, mounting solution that can keep our modules as cool as possible. Some ventilation is, if possible. In a solution like this, you can have, the back of the modules ventilated, and this will keep them cooler than if we have these modules completely stuck onto some surface. Yes, for instance, I know in some projects in the Arab countries,
yes,
in the Arabian Peninsula, very hot, very high temperatures, 50 degrees and higher. Some PV systems, they even consider some kind of refrigeration, some ventilation, some forced ventilation behind them. So you use part of the electricity they generate to try and ventilate the modules, okay? Because of this effect. Okay, in terms of the budget, in this case, there is a foreseen expenditure of 117,000 euros. So because there's no batteries, and thanks to the improvement of technology, in this case, the
Paul, this is not exactly the amount, because this is a calculation doing.
Yes, it's an estimation. I know. Yes.
And later I will show you the real budget. Oh no, I think that you have it in the presentation.
Yeah. So the expected payback period at the time when the design was done, 9.9 years. Okay, so almost 10 years. This was the design by Arnau. The expected. Okay, expected to be started up in March 2018. Okay. Then finally, this system was built or is being built, right?
Yes, we don't have photos of the finished installation because it is being executed just now. It starts 1 month ago, and maybe in 2 weeks will be working.
Exactly. It is being installed right now as we speak. Okay. So
okay, this is the real budget.
From the initial projections of 117.5 thousand euros, well, there's a bit of an increase, but not so much. 4,000 euros, and the rest is the taxes. Okay? The VAT, value added tax. But you can see, if we consider this investment cost, I mean, this is the turnkey cost, of 121 100,000 euros divided by 75 kilowatt peak, we have a reference investment cost of 1,600 euros. 1,600 euros per kilowatt peak, which is about even less than half of the cost of the installation in the system in the cemetery. Yeah, because of the batteries. There's no batteries here, but also because of the reduction also in the costs of PV modules and etc. Also because it's a bit of a bigger system. So after 4 years, we can see that also costs have reduced, have declined for the rooftop PV systems in general, in particular in Barcelona. Okay, so we have some time for questions or comments, if you like. We have some 15 minutes, 20 minutes maximum. If you want to comment anything, now this is the moment. Anybody?
Thank you for this presentation of two projects. It's always good to see real things on the ground. But one of the things that are important for us in Mozambique is how these policies are, pressured. You mentioned Barcelona moved from no permits to put back on the grid, and then now you are finally selling to the grid, buying from the grid. If you can elaborate a little bit more, I know that we have EDM people listening to this. EDM has been the monopoly for energy in Mozambique for many years, and therefore didn't allow much flexibility. Now, in the last few years, we see more flexibility. We see EDM going into renewables. Was not even a policy. When we talked 10 years ago about renewables, they didn't want to hear anything about it. But slowly it's coming. We see independent producers taking leads in the market share, but we don't see much on the regulation. So the private sector is more aware of opportunities to get involved in a business like selling to the grid or buying to the grid. I really like the idea of not having batteries, because batteries increase usually the price of the plant. So government should be more aware of these necessities. So maybe we can talk a little bit about your experience.
Yeah, of course. This is a very key topic. It's not easy, like any other regulatory aspect. Kemal, is not something that this is my opinion. That can be a quick change. It needs some evolution. In Spain, we have had ups and downs, right? Now, in the 90s, there was like a discovery of this, and then there were some policies that were supporting with feed-in tariffs very advantageously. Then at some point that was revised and reduced. Then after 10 years, 15 years, they were completely stopped. And then now we are going back to the path of allowing again the connection of small PV systems. In here, I think we need to separate the case of large PV plants, solar parks, solar farms, and this kind of system that we are seeing, the rooftops or the small. Let's say, to fix some reference, I would suggest the 100 kilowatt reference. Anything below 100 kilowatts, we can call it small, and probably it could merit a specific regulation or specific framework that could make it easier, more flexible. Then anything above 100 then could be treated perhaps in a more like a power plant concept. I don't know, or now you want to.
Yes, here in Spain, historically, the regulation of the renewable sector depended a lot of the connections between the governments and the electric companies. 4 or 5 years ago, we had a government that has a lot of connections with the electric companies, and they were doing policies for these electric companies. We can say that these electric companies were governing, and these electric companies doesn't want the renewable facilities because they prefer to keep the old model based in nuclear centrals, only in gas generation, and we here in Spain we have a lot of governance, ex-governance working now in electric companies, and this is because while they are in the government, they are doing laws for these companies, and since the change of government, we fight a lot here in our sector. We were fighting a lot against these laws that they were very restrictive with the renewable energies. And since the change of government, maybe 2 or 3 years ago, we get finally we win this fight that we were keeping maybe 10 years during 10 years, and we achieve a lot of things that we were fighting, like the facilities, or that now is very easy to connect and install a photovoltaic installation to the grid. For example, now we don't have to pay a tax for using the sun. This government that we had, they invent a thing that was called the sun tax, that they said that we had to pay for using the sun. And this is and here it was the only country in the world that we had this kind of tax, not for self-consumption, I am talking about. And it was a large fight of the sector. We were doing a lot of noise in the media, and this is a little bit our experience, our bad experience, but also a good experience, that if you fight for your rights, here you can get some things. And here we are now getting the results of this fight.
It has to be said, I think, that in the case of Spain, it's a particular situation. You had different positions from different administrations as well. The examples that
I don't know how it works in Mozambique. I can only talk about the situation of Spain and Europe in general.
Yes, I think it's different sometimes from the point of view, the political vision, the technical vision, and the business vision. Yeah, and sometimes it's not easy, to put this, harmonize this, and get everybody satisfied, and do it quickly. So I understand this necessarily will take some time in Mozambique. What I will probably recommend strongly is to do some projects, some demonstration projects. I wouldn't even call them pilot projects, because in Mozambique you already know about photovoltaics. So you don't have to pilot things. You know it will work. You know EDM. There's a lot of people who already have experience, good experience and knowledge with photovoltaic systems. You just need to start putting this experience into this kind of projects. This picture I have behind me, this is also a PV system in a museum. This in London. Okay, this is not Barcelona, it's London. So public facilities are probably a good starting point to demonstrate this kind of projects. The examples we shared with you today are two public places: cemetery, car park, in a road, motorways. This is a suggestion, but I really invite you, everybody in the room, EDM ministry, also from the private sector, to explore as a first step in Mozambique this possibility of demonstration projects. 50 kilowatt peak, 60, 70, not too big. This kind of projects, the grid connected. And why not use then in a later stage for the residential sector, where you can have some more evolution with the grid connection and the low voltage side of things with EDM. There's no other way to learn about these things rather than demonstrating, starting, break the ice. 1, 2, 3, and thanks to these demonstration projects, I'm sure everybody in Mozambique will learn, will adjust the mechanisms that are necessary, and I'm sure that in 5 years' time we'll be talking about this, and this will be a reality in Mozambique. Why? Because you have so much sun. At the same time, you have the knowledge for photovoltaic, and you have the consumption for that. You have all the necessary elements. Now, in this process of learning, it will be important to work with EDM, to work with the ministry, and probably with a regulatory agency to decide which will be the most simple or the best mechanism for Mozambique on how to deal with the electricity going in and out of EDM system or the grid. We have the net metering possibility, you have the net billing possibility, you can have, for instance, the model that we are following in Spain now, in the last revision 2 years ago, is that you have some compensation balance between what is injected to the grid and what is consumed. It's not net metering here. It's not that today I inject 1 kilowatt hour and then tomorrow I get it from the grid, same price. It's not like that. There is a compensation rate of about 1 to 3 in economic terms. I don't know, Arnau, if you want to mention about that or.
Yes, that was one of the demands of the sector, to get this balance, with the grid, and I agree with you all that it's important to start with small pilots like this one in Las Corts Cemetery, and because it's important for testing also the technology, also test the results, the expected results. Here, one of we in this bad season that we pass with the bad regulations, the public administrations, like the small public administrations, like the municipalities, they, for example, in Barcelona, our city, they did a lot of efforts for during this bad regulation, promote these pilots like Las Corts Cemetery, some other facilities that I work also, and we are using now the results of these pilots for now that we can do more things because we have a better regulation. We are taking advantage of these pilots that we did maybe 6 years ago when the regulation were very bad. And what you are telling about, it's also very interesting that it's important to work in doing this balance between the energy that we are getting from the grid and the energy that we are introducing with our facilities. No? Here, for example, in the residential sector, in the houses, thanks to this balance that we can do now, this compensation, we are doing a lot of PV installations in houses, because in houses we are working all day, we are outside home, and we are also producing energy. And now we can take some advantage of this energy that we are putting into the grid while we are not at home. No? And this is a very, very good thing. It must be better, eh? Like Paul said, we are getting maybe half of the price that we are that the tariff price, no? But it's a step, no? It's a step beyond, because 3 years ago we are getting no money for the energy that we were introducing into the grid. No.
Any other comment? I think this is a very, very interesting question. Any other? Anybody else wants to join in this comment? Any other opinion on the aspect of the balancing with the grid? Okay.
Means that there is no more questions.
Okay.
Is that okay? I know this is I mean, our course is mostly about technology and feasibility studies. Obviously, this question is very important, but it is more like framework, regulatory, and yeah, it will probably merit some more attention in another course. At the same time, there is a new electricity law being passed, and that will have to be operationalized in the coming months in the country. So I'm sure many of these issues are on the table and will be happening this year in the coming in the country, in Mozambique. The only thing I can insist on, or I cannot stop insisting on, is on the learning by doing. Demonstration projects is really the most effective way to put these ideas and concepts into kilowatt hours flowing in Mozambique and everywhere. Yeah. So that's the only recommendation I can insist on.
Yeah, thank you. It was good that you gave us this information of starting demo projects to make make a statement in a way, not proving anything, but testing the little things that are not fixed yet, or we don't know how it works. Yeah.
Yes.
Thank you.
The good thing about this, Kemal and colleagues, is that this kind of systems, the fixed parts, let's say the PV modules, the inverters, they will be working. It's the adjustment on the metering side, yeah, on the financial regime side. So even if you start with one approach, after 2 years, after doing your analysis with different stakeholders, this could be changed eventually. Yes. Especially if it is a demonstration project that is being led by the public authorities. So it can be adjusted after some learning conclusions. Yeah. So definitely, I think that's the way to move on with these aspects, rather than just staying still and not doing not progressing. Rooftop PV, net metering, net billing, everywhere in the world is happening. Yeah, I think I told you at the beginning of this course, we are also now doing with our company a study for the government in Ghana. We are doing the mapping of the public buildings to see what would be the type of PV systems, and we are establishing. We are creating some categories and some standardization. So you see, it's no longer the question: is it PV systems, adequate for public buildings in Ghana? No, the answer is yes. They are very adequate. They are needed. Now, move on. Next stage. Which kind of PV systems? How can we deploy large-scale program with the thousands of public buildings in a country like Ghana, which is smaller than Mozambique? So it is happening. It's not only in Spain and Germany. It is happening in African countries too. So it is a time for Mozambique also to join this and to learn in the Mozambican way. That's fine, but not to postpone anymore this aspect of solar PV systems. Okay. So unless there is any other comment or question, I think it will be time to leave it for today. Any other issue from anyone? No.
No questions.
So thank you very much, especially to my friend engineer Arnau Alarcón, that he has been very kind to join us today. And
thank you for your attention, and it was a pleasure for me.
Thank you, Arnau, and thank you, everybody. I'll see you again next week. We will go back to our normal routine of Wednesdays session from 9 to 11. So enjoy the rest of your week. I know tomorrow is a public holiday for you, so enjoy your day tomorrow, and we'll see you next week. Okay? Thank you very much.
Bye-bye.
Thank you very much, Paul.